Hello, colleagues. In this discussion, we are still proceeding with our series on combustion and fuels. And now, today, we are going to look at some important terms that we must note as we are dealing with combustion in thermodynamics. So, we are talking about thermodynamics. Now, the first term that we need to look at is what we call air-fuel ratio, and this refers to the ratio of the amount of air in combustion reaction with the amount of fuel. In other words, the amount of air that is reacting with the amount of fuel in a combustion reaction. So mathematically, it can be given by ratio of mass of air to ratio to mass of fuel. So AF, which is the air-fuel ratio, is equal to mass of air divided by mass of fuel. Now, it is the same as molecular weight of air times the number of moles of air divided by molecular weight of fuel times the number of moles of fuel. Because we know that the number of moles will always equal to the mass given divided by the molecular mass. So now, if I cross multiply, it means that the mass given for either fuel or air will always equal to molecular mass of the air or fuel times the number of moles of the same substance. So fuel-air ratio is the inverse of air-fuel ratio. So if I get 1 out of the AF, I'll get the fuel-air ratio. So the theoretical air-fuel ratio can be estimated from stoichiometric combustion analysis for just complete combustion, because we may need to determine this. So now this air-fuel ratio, we can determine it by getting the reactants, which could be oxygen and maybe the fuel, which could be carbon. So giving carbon dioxide plus, for example, maybe excess air and heat. So what is going to happen is that if we have enough air to cause complete combustion of the fuel, then we shall call that stoichiometric or theoretical combustion analysis. And it is through that we are able to determine the theoretical air-fuel ratio. Equivalence ratio is the ratio of actual, that is number 2, is the ratio of actual fuel ratio to the theoretical fuel-air ratio for complete combustion. So if we are looking at the actual fuel-air ratio vis-a-vis the theoretical fuel-air ratio for complete combustion, then we are talking about equivalence ratio. Now, you will find that if the fuel-air mixture, if this equivalence is less than unity, then we shall say the fuel-air mixture will be called the lean mixture. Then if we have the equivalence ratio value being greater than a unity, then the mixture will be a rich mixture. In other words, this is going to be having excess air, this is going to be having less air. So what will happen is that in the lean mixture, if you have less air, in the rich mixture, you have more air, and therefore the values of equivalence ratio will be varying. So it is important to understand the specific reaction that is taking place by carrying out the analysis, the stoichiometric analysis, you are able to determine the equivalence ratio. What about theoretical air? The theoretical air is that minimum amount of air that is sufficient, that is able to provide sufficient oxygen for complete combustion of the fuel. So you need to understand that amount of air, or the minimum amount of air sufficient to provide complete combustion of fuel, is called theoretical air. Complete combustion means complete reaction of all the oxygen present in the air. Uh, for example, if we are talking about a fuel that has carbon, then it has hydrogen, then it has sulfur, resulting into carbon dioxide, water, and sulfur dioxide. Nitrogen with air combustion products. Of course, if we also have nitrogen there and it is able to react, but in most cases, this nitrogen won't react, but it will be present in the byproducts, because we know air has oxygen, has nitrogen, and other gases like some water vapor, argon, we have neon, and many others, even dust. Of course, all those are components of air. But by percentage, we realize that nitrogen and oxygen take the significant proportion. And therefore, when we talk about air, we are always going to be meaning nitrogen and oxygen in our discussion in thermodynamics. So what about excess air? Excess air is any air supplied in excess of theoretical air. So if we supply air and it is in excess of the theoretical air, we say the theoretical air is the minimum that is sufficient to cause complete combustion of the fuel. So if after complete combustion of the fuel, we still have some air remaining, we shall call it excess air. Let us also talk about flash point and fire point. So flash point refers to that temperature at which vapor is given off from the liquid at a sufficient rate to form an inflammable mixture, but not at sufficient rate to support continuous combustion. So we have a temperature at which vapor is given off from a liquid fuel. If we talk about gasoline or diesel, so if we have air passing over this fuel and then it forms part of the vapor. So now the temperature that is required for this kind of fuel of vapor to become or to form an inflammable mixture, okay, and then not be able to, of course, support sufficient burning. It is not at a sufficient rate to support continuous burning. Then we shall call that temperature to be a flash point. So you need to understand this point. Then the fire point refers to the temperature at which vaporization of liquid fuel is sufficient enough to provide continuous combustion. So you may have this liquid fuel vaporizing, and then the mixture of that vapor and air reaches a temperature that is sufficient enough to, of course, facilitate combustion, and then there is continuous combustion of this mixture. We shall call that a fire point. So in the transport of liquid fuels, it is always important that you understand the flash point and fire point so that you avoid any hazard associated with explosion of that fuel tank. And we must note that these temperatures are not a measure of ignitability of the fuel, but of the initial volatility of the fuel. So what is adiabatic flame temperature. Adiabatic flame temperature refers to the temperature that could be attained by the products of combustion when the combustion reaction is carried out in limit of adiabatic operation of the combustion chamber. So in adiabatic operation, we are saying that combustion takes place in the absence of work, kinetic energy, and potential energies. The energy released during combustion shall be carried by the combustion products within minimum or no heat transfer to the surroundings. In other words, when the combustion takes place in the combustion chamber, for example, in an internal combustion engine, this adiabatic flame temperature is that temperature that is attained when you have no heat transfer to the surroundings. When no heat is lost to the surroundings, at that temperature, that maximum is what we are calling adiabatic flame temperature. This maximum temperature is attained in the combustion chamber and is a very useful parameter for designers. Of course, we need to understand that when in an internal combustion engine this happens, then the material, if we are designing, for example, a piston and the engine broke, you must make sure that the material that you are using to design should be able to withstand this maximum temperature called adiabatic flame temperature coming from the combustion of fuels in the combustion chamber. Let us talk about also what we call wet and dry analysis. Combustion analysis, when carried out considering water vapor into account, is called wet analysis. But when we do not consider the water vapor, or when the analysis takes an assumption that vapor is removed after condensing it, then we shall call it dry analysis. Let us also talk about volumetric and gravimetric analysis. Volumetric and gravimetric analysis, we are going to look at analysis of the products of combustion by volume and by gravimetric. By volumetric is when we are talking about the volumes of the products vis-a-vis the reactants. Then gravimetric analysis, we are talking about the measure of the reactants by mass in kilograms and also the measure of the products by mass in kilograms. Combustion analysis carried out based upon percentage by mass of the reactants and products is called gravimetric. So this is what we have just said. Now another point to note is the pour point. The pour point refers to the lowest temperature at which liquid flows under specific conditions. Yeah, so you must also note that. Then the cloud point is when some petroleum fuels are cooled, the oil assumes cloudy appearance. This is due to paraffin wax or other solid substances separated from solution. The temperature to which cloudy appearance is first evident is what we are calling the cloud point. Composition of air, we have to understand that atmospheric air is considered to be comprising of nitrogen, oxygen, and other inert gases that we said. There is argon, there is neon, and also some water vapor. So for combustion calculation, the air is considered to be comprising of nitrogen and oxygen in following proportions. A molecular weight of air is taken as 29. Okay, a molecular weight of air is taken as 29. Now, composition of air by mass is oxygen at 23.3% and plus nitrogen at 76.7%. 23.3% oxygen and nitrogen 76.7%. That is composition by mass. What about composition by volume? Oxygen is estimated at 21% and nitrogen at 79%. So that one is done. Let us talk about enthalpy of combustion. So the enthalpy of combustion is actually the amount of heat produced when 1 mole of a substance is burnt to produce its constituent products of combustion. It can also be the enthalpy. It can be the difference between the enthalpy of the products, the heat um, contained, or that the reactants and products contain, but of course they are different. So difference between enthalpy of the products and enthalpy of reactants when complete combustion occurs at a given temperature and pressure. It may be given as a higher heating value or lower heating value. Shall see what these values mean. A higher heating value is the enthalpy of combustion when all the water formed during combustion is in liquid phase. Then the lower heating value of fuel refers to the enthalpy of combustion when all the water formed during combustion is in vapor form. So the lower value will be less than higher heating value by the amount of heat required to evaporate water. That is the latent heat of evaporation or vaporization of water. So if I add it to the lower heat value, the lower heating value, I would get the higher heating value. It is also called the calorific value of fuel and is defined as the number of heat units liberated when a unit mass of fuel is burnt completely in a calorimeter under given conditions. What is the enthalpy of formation? Enthalpy of formation is the energy released or absorbed when a compound is formed from its elements at standard reference state. The standard reference state in most cases has always been considered to be 25 degrees Celsius or 298 Kelvin and 1 atmosphere. Thus, enthalpy of formation shall equal to heat transfer in a reaction during which compound is formed from its elements at standard reference state. Enthalpy of formation will be positive if formation is by an endothermic reaction. That is, heat is absorbed from the surroundings and the product is formed. When it is negative, then heat has been given out. That is during an exothermic reaction. We have said the standard reference state refers to the thermodynamic state at which enthalpy datum can be set for studying reacting systems. The standard reference state, zero value is assigned arbitrarily to the enthalpy of stable components. And for example, oxygen, it would be 0 if it is existing as a molecule. Hydrogen, if existing as a molecule, it would be 0. But it will not be 0 if it is existing as an atom. Generally, the standard reference state is taken as 25 degrees Celsius and 1 atmosphere. That is what we have already said. Or 298.15 Kelvin, and the reference pressure is 1 atmosphere. So we need to also understand what we call dissociation. Dissociation is basically applicable when you have the products of combustion or the products of a reaction disintegrating into their constituent reactants. For example, we may have carbon dioxide disintegrate or dissociating into carbon and oxygen. Of course, this shall happen with the release of heat. Now, not release of heat, but of course with absorption of heat. Now, if we are talking about combustion, here these are reactants and these are products. So what happens here? You have carbon plus oxygen giving you carbon dioxide, of course, plus heat. This is the heat that we use for different purposes. So this equation is balanced. It's very balanced. Now, what if this is now combustion? Combustion, of course, it is a reaction, a chemical reaction in which a fuel, a combustible fuel, is burnt into its byproducts, of course, with a result of release of heat, or the process by which heat is released from a fuel, a combustible fuel, by, of course, reacting with oxygen to release byproducts. Now, dissociation here would, as we have already said, we will have heat of carbon dioxide to release carbon plus oxygen. So you have carbon dioxide releasing carbon plus oxygen. This comes as a result of absorption of heat. And this is now an example of an endothermic reaction. So a reaction that takes place with absorption of heat from the surroundings. Thus, general dissociation has inherent requirement of high temperature and heat. Yeah. So, ladies and gentlemen, we have talked about a number of terms that are very important to understand as we enter into our series of combustion. Thank you so much for listening.